of Space Education and Research Foundation, and on my personal behalf, it is my great pleasure to welcome Professor Arup Das Gupta, the speaker for this webinar on satellite communication. This webinar is going to have 4 modules, and today is the first module, and this is on fundamentals of radio communication. Before I hand over the mic to Professor Arup Das Gupta, I would briefly introduce him to you. Professor Arup Das Gupta obtained his Masters of Engineering in Electrical Communication Engineering from Indian Institute of Science, Bangalore in 1970. He is currently managing editor of Geospatial World magazine and was adjunct faculty in 2 institutes, DAIICT and CEPT. He has a very long 48 years of experience in satellite communication, remote sensing and GIS technology. He retired from Space Application Center as a Deputy Director of SATCOM and IT Applications area in 2005, and he has also, after that he has served as Independent Director in ScanPoint Geomatics from 2009 to 2014, and as a Distinguished Professor from 2005 to 9 at BISAG. For his significant contribution, he received Excellence Awards from Indian Society for Remote Sensing in 2005, and in 2016 he received the Excellence Award from Indian Society of Geomatics. He is also a recipient of Geospatial Lifetime Achievement Award in Geospatial Technologies for 2009 and Astronautical Society of India's Award for Space Science and Applications for 2000. He is a senior member of IEEE, Fellow of IET, Fellow of ISG, and life member of INCA and ISRS. His current interests are space policy, convergence of space and information technologies for sustainable development of the Earth planet. With these few words, it is my pleasure to invite Professor Arup Das Gupta to deliver his talk on fundamentals of radio communications.
Thank you, Dr. Dutt, for that very nice introduction. To all the guests who are logged on to this program, we have turned this program in 4 parts, and today will be the first part in which we will be essentially talking about the fundamentals of radio communication. Why I am doing this is because space satellite communication is a special case of radio communications, and therefore we need to understand what is it in radio communications that is important, and then we can link to satellite communications in subsequent lectures. So let's go ahead. So this is what the module will consist of. We will have a very short history. Then we will talk about radio waves. We will talk about the radio spectrum and the classification of radio bands. We will talk of radio wave propagation, the effect of ground, atmosphere, ionosphere, troposphere, and then we will look at how we can add information to radio waves, and that technique is called modulation. And last but not least, we have to look at the radio frequency noise which surrounds all of us, and it has a deleterious effect on radio wave signal reception unless we are careful in our design of our systems. So, the history. In 1864, an English scientist by name of James Clerk Maxwell, he propounded 4 equations to show theoretically that the relation between electric and magnetic fields and the common nature of light and electromagnetic waves. Which means what he said was that electrical and magnetic fields do not exist independent of each other, they exist together, and light is one such electromagnetic wave. In 1888, a person by name of Heinrich Hertz, a German, he demonstrated the generation and detection of electromagnetic waves. Okay, so Maxwell was theoretical, Hertz was practical. And I'd just like to say as an aside, today when you talk of megahertz or gigahertz, remember that Hz, that Hz is of Heinrich Hertz, who demonstrated that you can generate radio waves and detect them. Then comes in 1894 our own scientist Jagadish Bose, and he demonstrated how this could be used practically. He rang a bell in another room, or he set off a little firecracker in another room. So these were very practical applications of waves, right? But then Jagadish Bose was basically an inventor and a scientist, so he never took this forward. The person who took it forward was an Italian scientist, or rather I'll say Italian innovator, by name of Marconi. And Marconi in 1896 demonstrated that you can do telegraphy by wireless. As you know, in earlier days when you wanted to send a telegram, you had to go to the post office and there was this pair of wires going out from there, and then the person would take your message and you would tap on a switch and spell out words which are combinations of small taps and large taps. So they are also called dots and dashes or bits and bars, right? So he was able to demonstrate that you could do telegraphy not by using wires but by using radio waves in a wireless manner. But his crowning glory was he demonstrated that you could do it transatlantically. He set up a transmitting station in Ireland and a receiving station in the US in a place called Scotia, and he could send a message from Ireland to Nova Scotia where it was received. It was a very simple message, and that message is, all of you may be familiar with, it's dot dash that's SOS, and that is the shortest kind of message that you can have. Okay, so that's all about history. Now let's get on with our other subject. So what Marconi said, what Maxwell said is that the two waves, that is the electrical wave and the magnetic wave, are tied together, and you can see how they are tied together, and it travels at the speed of light. Now this is a very interesting, because as you know the speed of light is constant. Okay, so we also now define a term called lambda or wavelength, right? What is the wavelength? The wavelength is the distance between two consecutive peaks of the signal. And then we define the frequency as c divided by lambda, right? So the megahertz is equal to speed of light divided by wavelength. And you must choose the correct units also. Okay, so with this very fundamental this understanding, let us now go a little beyond and look at the electromagnetic spectrum, and it is fantastic. The electromagnetic spectrum extends from rays, X-rays, ultraviolet rays, visible light, to infrared, to microwave, and to radio waves. So as you can see below, The gamma rays are very high frequency. In fact, the high frequency is so much that we don't talk of gamma rays in terms of frequency, we talk in terms of wavelength. In fact, even in microwaves, when you go to very, very high levels of microwave, we talk in terms of millimeter. Like for example, 4 millimeter waveguide or millimeter like that. But then as you go into higher and higher frequencies, then you start talking in terms of the frequency, which is the hertz. So this gives you an idea and what are the kind of things that are there. So you have all these examples which I will not dwell too much upon, but you understand from this that the electromagnetic spectrum is a fantastic spectrum and it is of great use not only for radio communication, many other things. So now an interesting thing again we see if you look at the top in this frame, what you see is how opaque is the atmosphere. And we find that the atmosphere is very opaque till it reaches the visible, and which is a great thing because rays and these rays, they are very dangerous. They can cause cancer, and therefore our atmosphere protects us from these high frequency waves, dangerous waves. We have a window where at the visible, and think about it, all the beautiful things that you see, all the light that you can think of, your photography, everything is dependent on this little window which has been provided in the Earth's atmosphere, right? Then again you have small windows, and these are called the infrared windows. We will not talk about this because it is more important for remote sensing, so I will not spend my time on that. And then you see again there is a big window, right? And this is that window where we are able to use radio communications, particularly with satellites. So you see the slide at the bottom. Here you can see how the various, so you have telescopes which can look in the optical side. Then you have infrared satellites for infrared sensing, which is again more related to your remote sensing. And then here is our nice big gap. Okay, so let's go ahead a little bit more. So what do we talk of the radio spectrum, right? So if you see here, you see roughly where the radio spectrum starts, okay, not 1 centimeter, a little more, maybe 4-5 centimeters, and goes all up to 10 to it's a logarithmic scale. So how do we arrange these, right? So how we arrange them is, you see on top the frequencies, right? And in the bottom you have the radio spectrum as defined originally. So you have up to about 1 kilohertz, you have what is called very low frequency. Is used for communications from submarines which are in the water. Then you have 10 to 100 kilohertz, which is for long wave, and over the time they didn't have all these satellites and all, so people used to actually use long wave radio to get signals from far off places. Then you have the medium wave, which is 10 to 100 to 1 megahertz. This is very common for you. And then you have the high frequency, which is from 1 to 10 megahertz. Then you have the VHF, which is from 10 to 100 megahertz. The UHF, that's the ultra high. VHF is very high frequency, UHF is ultra high frequency, right? And you can see the corresponding frequency. Then you have super high frequency, that's from 1 gig to 10 gig. Then you have the extra high frequency, which is 10, 100 gig. And beyond this, which is 1 kHz, this is all infrared, and again you are not. And again, we are not going to spend our time on this, right? Okay. So let's again look at how the radio spectrum is used. So you have again, as I said, very low frequencies are used for maritime radio and navigation. Maritime radio and navigation is also using long wave frequencies. Then the amplitude modulation radio, aviation radio, navigation all use medium frequency. Shortwave radio use high frequencies. VHF television and FM radio uses very high frequencies. VHF television, mobile phones, GPS, Wi-Fi, 4G, these are all using UHF. SATCOM is essentially used in the SHF. But I would like to point out to you, it is not necessary that SATCOM is only restricted here. Sometimes SATCOM does get into UHF also. Okay, so these are not so cut and dry. Okay, so now there is another so there is now another complication. We have all these VHF, SHF, etc., etc. But satellite communication people want to talk in terms of UHF, L band, S band, C band, X band, KU band, Ka band. Right? And you can see the breakdown of those, and they're pretty funny. There is no logic to it. So 1 to 2 is L band, 2 to 4 is S band, 8 is C band, and 8 to 12 is X band, 12 to 18 is Q band, 27 to 40 is Ka band. Right? So I just put over here the EHF and the SHF just to be able to map this nomenclature, which we will be now using henceforth in satellite communication, to the standard scientific method of SHF, VHF, and etc. etc. Okay. Right. So now let's go to the next. Okay. Again, we are using the atmosphere, and remind you, the atmosphere is actually having several portions. For example, you have the troposphere, then you have the stratosphere, then you have the mesosphere, and then you have the thermosphere, right? And here you can see the kind of satellites which are being used for this. Even aircraft are using it, and this is our radio. We have the radio communications. Okay, so this is, and now why I am reading these is because these parts of the atmosphere have effect on the radio waves, particularly coming from the satellite. We will discuss about this a little later in the lecture. So, what is the effect of the atmosphere? So, atmosphere gives rise to losses. First of all, the atmospheric gases absorb the radio wave energy, so the signal gets reduced. Then, if you have adverse weather condition, heavy rain, high rain rate, then also certain frequencies which are in the KU and KA band are also affected. Luckily, adverse weather conditions don't affect C band or so forth. X band a little bit perhaps, but major effect is on KU and KA. Why I say this is because KU and KA are now the preferred bands for everything from direct to home transmission of television signals to direct to home internet connectivity. We'll talk about this later. So ionosphere again induces signal fading and distortion. Why? If you know the ionosphere is made up of free electrons, right? So these electrons then interfere with the signal and actually bend it. You know, like you have, if you take a pencil and put it in a glass of water, the pencil bends. Same way, the signal bends, and because of that, you get the signal fading. And because the ionosphere is dynamic, so the bending is not always the same. Right? Then there is troposphere, and that again causes signal path to bend. So you see, while the atmosphere is also good for us in some ways, but in some ways it really acts as a negative thing, and we have to really work hard to be able to overcome this. We will see this in some other lectures. So we are sending radio waves. The radio wave doesn't contain any information, right? So how do I now add information? Now I'll go back to Marconi, and what he did was, he said every dot is a short burst of radio wave and every dash is a burst of radio wave. So he was sending the message by some technique called on-off frequency modulation. Of course, nobody uses that now, but in those days, this was the method that he could do. Today, the things are much more complicated because you have a lot of information. You have voice, you have text, you have data, you have internet, you have TV. It's just too much, multimedia. So how do I handle all this? So there are two types of ways in which you can impose your information onto the carrier wave. So the RF wave is called a carrier, right? And on the carrier you impose your wanted signal, and that technique is called modulation. And at the receiver, that the information is removed from the carrier, and that is called demodulation. Okay, so analog, initially everything was analog. Okay, so what you did was you basically changed the height of the radio wave such that it would follow the signal pattern, right? The information signal pattern, which would be, let us say, with audio, or if it is what you call data. The data would be digital, but audio would be analog. Right? Now you have two types of modulation. One is called the amplitude modulation. The other is called the frequency modulation, and there is a third one called the phase modulation. In digital, because you are dealing with digits in terms of pulses, so again amplitude modulation is very rarely used, but you do use frequency and phase modulation, and these are the most common methods of adding information to the carrier. So what is amplitude modulation? Okay, the radio frequency wave is called a carrier frequency, or RF, right? The information is called a signal. The information that you want to convey is called a signal. Amplitude modulation is achieved by superposing the signal on the RF such that the amplitude of the RF, the carrier, varies according to the proportion of the signal that you want to send. And AM is very commonly used in terrestrial radio. All your AM, FM radios are all basically using, rather AM radios are using amplitude modulation. And even in TV earlier, not now, earlier the picture was in amplitude modulation, but not now. Now everything is changed, everything is digital. So what do you do in the frequency modulation? In the frequency modulation, what you do is you vary the frequency of the carrier in consonance with the information that you are sending, right? So the amplitude of the carrier does in amplitude modulation, the amplitude of the carrier changes, but in frequency modulation, the amplitude of the carrier remains the same. It's only the frequency that shifts up and down, right? And FM is used in terrestrial radio, of course you know, and TV sound. But again, many of these things are being phased out in favor of digital technology. Therefore, if you have to have an analog satellite transmission, then always you use it. In fact, in 1974, when we were working on a direct-to-home TV broadcasting, we were using a satellite which NASA had loaned us. It worked in the UHF range, and the picture was amplitude modulated, sound was frequency modulated. Talking of 1974, way back history. So here is how they look. I have the modulating signal. I have just picked a very simple signal, maybe a 1 kilohertz tone, and this is how your carrier will vary if you do an amplitude modulation, right? Exactly following the envelope. If you do a frequency modulation, then again you see how the frequency instantaneously changes, but the amplitude does not change, right? Now we come to the digital part, and that's really very interesting for us, because today everything is digital, right? So suppose I have a signal like this 01101. So I can look at the digital signal in this way. Okay, so 0 is no pulse, 11 is high pulse, 0 again low pulse, and again 1 is high pulse, right? And I have the carrier, right? How do I compile? Well, there are three ways of compiling it. This is what we call the amplitude shift gain. Okay, so what you do is, based on the height of the signal, you change the amplitude of the carrier, and that's what you can see over here. So 0 is reduced, 1 is high, 1 is high, 0 is reduced, again 1 is high. But this is a pretty silly way of doing things, because again you have noise which will disturb you. So really what we do is we use something called frequency shift gain. That is, one frequency represents the 0, another represents the 1, and again 0 and 1, right? But another interesting method, and this is very very common now in satellite communication, is phase shift gain. If you remember, I talked about phase shift gain before. In this case, phase shift gain is very very important. So you see, here is the 0 phase, the 1 phase exactly opposite, the other phase exactly opposite, 0 exactly opposite, and 1 is exactly. But frequency shifting is perhaps one of the most important modulation methods that we are using, and there are a lot of complications there, which I am not going to cover all this, because that is a subject by itself. But you need to understand that when you have a digital signal, the best method is QPSK by PSK and then FSK. Right? Okay. So now let's talk a bit about the bandwidth. Right? Everybody talks about bandwidth. Right? What is this bandwidth? You see, when a carrier frequency changes, then what happens? It occupies a slightly larger position in the spectrum than just a single carrier. The single carrier will be just one peak. Whereas once you modulate it, either by PSK or by FSK, then it tends to cover a larger frequency band. Right? Now, AM signals require a bandwidth which is twice the modulating signal. So normally in AM, let's say if you have broadcasting, the highest frequency in a voice broadcast is roughly, let us say, 10 kilohertz. So an AM signal will have 10 plus 10, 20 kilohertz around the carrier, right? The carrier is resistor, minus 20 and plus 20. In FM, that requirement is much higher, okay? And in digital signals, the bandwidth requirements are very complex, but less than FM, right? And more than AM. So you have in phase modulation, you fall somewhere between the FM, FSK and amplitude. Okay. So now let's talk a little bit about the RF noise. You can't avoid noise. Noise is all around you. So all radio signals are corrupted by RF noise. Where do they come from? Cosmic noise. There is a continuous chatter If you buy mosquito or radio to a place where there is no railways and there is no transmitting station, you will hear what is that? That's noise, RF noise. The receiver is picking up and demodulating. Cosmic noise also comes from celestial bodies. All celestial bodies generate noise. Even the sun generates enormous amount of noise, and so does all the other celestial bodies, including the moon and Earth. Earth also generates a lot of noise. Then you have the thermal noise, which is generated by the circuitry. So every electronic component has in it devices in which the electrons are in random motion. Any object which is at a temperature higher than 0 degrees Kelvin will have the electrons some sort of random motion, and this random motion results in noise. That's why when you make a very good amplifier, you make sure that the input of an amplifier is very, very low noise. You can do it using special devices, special transistors, special ICs, and so forth. Then you have bandwidth noise, and this is basically coming from electrical appliances, mixies, cars, and so forth. And the RF noise increases proportionally with the bandwidth of the system. That's understood. The more the bandwidth, the more noise gets in. Right? So you have to keep your bandwidth low, but at the same time you have to take care of the noise. So what is the impact of the noise? We define a property called the signal to noise ratio, right? And this is a measure of the quality of the receiver. Okay. Now, amplitude modulation requires low bandwidth, but is more susceptible to noise because the amplitude of the modulated range is affected directly. So, amplitude modulation systems are highly prone to noise. FM and phase modulation require much more bandwidth, more than amplitude modulation. The phase modulation is a little less than FM, but FM requires a lot of bandwidth. But the immunity is because the signal content is not in the amplitude, but in the frequency or phase, right? So the carrier is remaining constant, doesn't get affected. The moment you detect the signal, you are able to get rid of the noise. Okay. So if we have a comparison of frequency modulation and amplitude modulation, so FM receivers have better noise immunity than the AM receivers. Noise immunity can be improved by increasing the frequency deviation in FM, but in AM no such option exists. Bandwidth requirement is greater and depends on the modulation index. Bandwidth is less than FM, doesn't depend upon any modulation index. Modulation index is basically how much you are you are imposing on the carrier, right? Then FM or PM transmitters are more complex than AM, but AM transmitters and receivers are less complex, obviously. All transmitter power is used to FM in very high efficiency. Power is wasted in transmitting the carrier and double sideband but let's not worry about it. This is more detail. So how do you choose the satellite communication frequencies? As I said, they are mainly in the UHF, SF and EHF, right? And the higher bandwidth at higher frequency bands, that stands to reason, right? The higher the frequency, the more space you have for the bandwidth. The preferred modulation techniques are FM for analog signals and different types of phase shift being for digital signals. You may have heard of the terms like BPSK, QPSK, and so forth. These are all different varieties of phase shift modulation. We will not go into the details. The modern satellite communications use digital modulation and because all media is now digital, right? So, in summary, what have we learned? We have learned about electromagnetic extend from gamma rays to long wave radio. Radio waves are a subset of electromagnetic waves. Radio waves are affected by the atmosphere. Radio waves can carry information like audio, video, and data using modulation. Amplitude, frequency, and phase modulation can be used. RF noise degrades modulated RF carriers. Applications have to balance signal to noise ratio, bandwidth, and circuit complex to decide which modulation technique to use. So this, in short, is a very brief introduction to the radio communications as such, without getting into satellite radio communication. Our next lecture we will start talking about that, right? So this is the end of the lecture, and if there are any questions, then bring up the box, and we welcome if any questions are asked to me.